In this video, we're going to be discussing the charge balance approach to pH calculations. So we have a problem. Write a charge balance equation for a solution of H2CO3, which is carbonic acid at 24 degrees Celsius. Then write the equation in terms of the total carbon concentration, CT, and expanded alpha values. So we're going to begin by writing the charge balance equation. And in order to do that, it's important to know the law of electroneutrality, which states that in any ionic solution, there is a net neutral charge, which means that the concentrations of the positive cations must equal the concentration of the anions in terms of charge. And so a way to express this mathematically is that once again, the concentration of the positively charged ions will equal the concentration of the negatively charged ions. And in an aqueous solution of carbonic acid, there are four ionic species. There is hydronium, hydroxide, bicarbonate, and the carbonate ion. And hydronium is a cation and the rest are anions. So in the equation, we can put hydronium on the left side of the equation with everything else on the right side of the equation. And so we can include the rest of the ions now. So hydronium equals X times the concentration of hydronium plus Y times the concentration of bicarbonate plus Z times the concentration of carbonate ion. And so in order to find out what X, Y, and Z will equal, we need to know how many hydronium ions will come from each of these anionic species. And so because hydroxide comes from the autolysis of H2O, there will only be one hydronium per hydroxide ion, so X must equal 1. And there will be one hydronium ion that comes from the dissociation of the first proton of carbonic acid, so Y will also equal 1. And there will be two hydronium ions that come from the dissociation of both protons of carbonic acid, so Z must equal 2. And so putting all of this into our equation, we get the concentration of hydronium equals the concentration of hydroxide plus the bicarbonate concentration plus 2 times the carbonate ions concentration. And now we can begin to rewrite the charge balance equation to include alpha values. But first of all, we need to know what an alpha value is. And so an alpha value is simply a mathematical expression, which is a fraction where the numerator is the concentration of some ion that would result from the dissociation of the acid or base divided by the analytical concentration of that acid or base. And so, for example, we can say that alpha 0 of carbonic acid would be the fraction of the actual carbonic acid molecule divided by the analytical concentration of carbon. And alpha 1 would be after one proton has dissociated, so the concentration of bicarbonate divided by the analytical concentration of carbon. And alpha 2 would be after two protons have dissociated, so the concentration of the carbonate ion divided by the analytical concentration of carbon. And so you'll notice that these alpha values are numbered such that their numbers represent how many protons have dissociated from the parent ion, and this will be true for any alpha value expression. So that means that the alpha value multiplied by the analytical concentration of the parent molecule will yield the concentration of that ion. So if we multiplied the alpha 1 expression by the analytical concentration of carbon, we would obtain the concentration of the bicarbonate ion. And similarly, if we multiplied the alpha 2 expression by the analytical concentration of carbon, we would obtain the concentration of the carbonate ion. And so now we can rewrite the charge balance equation. So our original equation, as stated in the previous slide, is hydronium equals hydroxide plus bicarbonate plus 2 times the carbonate ion. And so we can rewrite that to include the alpha values. So hydronium equals hydroxide plus alpha 1 times the analytical concentration of carbon plus 2 times alpha 2 times the analytical concentration of carbon. And we can further simplify this by factoring out the analytical concentration of carbon, and that yields this equation shown at the bottom of the slide. And so now we can begin to expand the alpha values, but first of all, why would we want to expand the alpha values? Well, whenever we expand the alpha values, we get all of the concentrations in the alpha values written in terms of a single unknown, and in that case, and in most cases, that single unknown is the hydronium ion. And the reason why that's useful to us is because whenever we're considering acids and bases, we want to know what the pH of a solution is given an analytical concentration of some acid or base. And so the first step is to rewrite the concentrations in terms of one of the ions, with the ions being either bicarbonate or the carbonate ion, along with the hydronium concentration. And so we'll rewrite in terms of the bicarbonate ion to start with. So writing our equilibrium expressions for each of the dissociations of carbonic acid, we have K1 equals the product of the bicarbonate concentration times the hydronium concentration divided by the concentration of carbonic acid. And then for the second proton dissociation, we have K2 equals the product of the carbonate ion and the hydronium ion divided by the concentration of bicarbonate. And so now we can begin to rewrite the concentrations in terms of bicarbonate and hydronium. So taking the first dissociation, we have, once again, K1 equals HCO3 times H plus divided by the carbonic acid concentration. So we'll multiply both sides by the carbonic acid concentration, which will yield that equation. And then we can divide both sides by K1. And we've now isolated the carbonic acid concentration, and it is in terms of hydronium and our desired ion, which is bicarbonate in this case. And we'll do the exact same process for the second dissociation. So we have K2 equals CO3 2 minus times H plus divided by the bicarbonate ion concentration. So we can multiply both sides by the bicarbonate ion concentration, which will yield that equation. And then we'll divide both sides by the hydronium concentration, and we are done now since we have isolated the carbonate ion concentration, and it is rewritten in terms of only the hydronium concentration and the bicarbonate ion concentration, which is what we want. And so now what will we do? Well, we need to notice that alpha 0 plus alpha 1 plus alpha 2 will all equal 1. Because these are all the fractions of the analytical concentration of carbonic acid. There's no way to destroy or gain any more of this, and so if you combine all of the fractions, naturally they will equal 1. And so if you multiply if you multiply this equation by the analytical concentration of carbon, then we will obtain the concentrations all add up to equal the analytical concentrations of carbon. And so using that expression, we can replace the concentrations with the isolated concentrations that we obtained, where we isolated the concentrations and rewrote them in terms of bicarbonate and hydronium. And this is our new expression for the analytical concentration of carbon. And so it's in terms of one of the ions, which is bicarbonate, but our end goal is to only have it in terms of hydronium. So how will we do that? So we can begin to rewrite it in terms of hydronium now. And the way that we'll do that is we take the equation that was shown in the previous slide, and we can divide both sides by the bicarbonate ion, and that will yield that equation there on the left. And then we can we notice that after we've divided both sides by bicarbonate, the expression on the right hand side of the equation becomes the analytical concentration of carbon divided by the concentration of the bicarbonate ion, which if you're observant, you'll notice that that's simply the reciprocal of the alpha 1 value. And so in order to get it back to being just alpha 1 rather than the reciprocal of alpha 1, we can take the reciprocal of both sides. And in doing that, we obtain alpha 1 equals 1 over hydronium divided by K1 plus 1 plus K2 divided by hydronium. And so what can we do to make this a little bit simpler and easier to look at? We can multiply both the numerator and the denominator by hydronium times the first dissociation constant. And whenever we do that, we get alpha 1 equals K1 times the hydronium concentration divided by the hydronium concentration squared plus K1 times hydronium concentration plus K2 times K1. And so that concludes our expansion of the first alpha value term. And so now alpha value 1 is written only in terms of one unknown, which is hydronium. And so even though it looks like it has more unknowns with K1 and K2, we know the dissociation constants of carbonate and carbonic acid and all those things, and so that's why they're not considered unknowns. The only unknowns in this equation is hydronium. And so now that we've rewritten alpha 1 in terms of the hydronium ion concentration, we want to do the same thing for the carbonate ion. And so following a similar process for the carbonate ion, I haven't included the steps here because it's extremely similar and it would be redundant. It would yield alpha 2 equals K2 times K1 divided by the hydronium concentration squared plus K1 times the hydronium concentration plus K2 times K1. So there is something to notice about these expanded alpha values. So alpha value 1 and alpha value 2 are shown side by side here, and it should become apparent that these have the same denominator. These have the same denominator, and this will apply to all alpha value expanded equations. So whether you're doing it for carbonic acid or phosphoric acid or sulfuric acid or anything like that, um, each of the alpha values within those acids or bases will have the same denominator. And then another thing to look at is the numerator. So in alpha 1, the numerator is K1 times H plus, and alpha 2, it's K2 times K1. And if you're observant, you'll notice that these are simply terms taken out of the denominator. So for alpha 1, K1 times the hydronium concentration. If you look in the denominator, right below it, there is K1 times the hydronium concentration. And then similarly for alpha 2, there's K2 times K1. And if you look in the denominator, that's simply a term from the denominator, because in the denominator, you also see K2 times K1. And so this rule can be applied to any of the alpha values. And so let's say that we wanted to obtain alpha 0, it would simply be, first of all, the same denominator, and second of all, it would just be the very first term that you see in that denominator. Since alpha 1 used the second term and alpha 2 used the third term, alpha 0 will use the third term in that denominator, which is the hydronium concentration squared. And this doesn't require any algebra. This applies to all alpha value equations, like I stated. And there are general equations for coming up with the alpha value equations, and it applies to all acids and bases. So what are our next steps now that we've expanded the alpha values? Well, we can rewrite the charge balance equation using the expanded alpha value expressions that we just obtained. And so we find that after substituting in for alpha 1 and alpha 2, the expanded expressions for each of those, we find that the hydronium concentration equals the hydroxide concentration plus the analytical concentration of carbon multiplied by alpha 1 plus 2 times alpha 2. However, we still have one unknown, which is the hydroxide concentration, but we want to find a way to write this in terms of hydronium. So in order to do this, we'll recall that the ionization constant of water follows the equation the hydronium concentration times the hydroxide concentration equals the ionization constant of water. And so that means that the hydroxide concentration equals Kw divided by the hydronium concentration. And at 24 degrees Celsius, Kw will equal 1.00 times 10 to the negative 14th. And so substituting this newly calculated expression for hydroxide into the charge balance equation, we get the hydronium concentration equals Kw divided by the hydronium concentration plus the analytical concentration of carbon multiplied by alpha 1 plus 2 times alpha 2. And I know that my video is cutting off the equation at the bottom right here a little bit. However, the only thing that's changed between this one and the above equation is the substitution of the hydroxide expression. And so this is our final expanded answer. And this is a really useful skill to learn to rewrite all of these charge balance equations in terms of alpha values, because once you have a single unknown variable and that unknown variable is the hydronium concentration, this can be used to very rapidly calculate the pH of solutions of polyprotic acids or bases based off of the analytical concentrations of those acids or bases. Not to mention that this can be used for mixtures of different acids and bases, and using a solving algorithm like GOLSEEK with Excel or Solver with Excel or any other polynomial solving algorithm, it makes for very rapid calculation of pH and pOH.